A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Welcome back, students. Today we'll continue with our discussion on outlining variables, measurements, and sampling plan. We've already completed the variables part and the measurements part. And today is the last part of this particular group, which is arriving at a sampling plan. So, putting things in context, this is the, the flow diagram that you are following, and we've reached the last sub block of the second big block. So we've already done the variables and hypothesis part. Then we've defined each of our variables operationally and conceptually, and we've also decided measurements for each variable. Today we'll see how we have to arrive at the sampling and data collection plan for our study. Okay, so what is sampling? Before we look at what is sampling and how it is done, let's look at a very fundamental concept that influences sampling, and that is the concept of central limit theorem. Yeah, it is a theory that states that given a sufficiently large sample size, the mean of all samples from the same population will approximately equal to the mean of the population. So in other words, if you collect enough data, your mean, that is the mean of your sample, would be approximately close to the mean of the entire population. And you can also read another law called the law of large numbers, which again says the same thing in another way, which says that this law, the central limit theorem, it kind of applies to large numbers only. You cannot apply this theorem to small numbers, which means you cannot collect like 10 or 20 samples and then assume that whatever mean you get is the mean of the population. So the central limit theorem, it forms the foundation of almost all tests that we conduct under the random sampling random sampling procedures. All the tests that you usually see in software that are for continuous numbers, or which are basically based on the normal distribution, they follow, or they are kind of standing on central limit theorem. So the diagram that you see on the right side of this slide, it actually says that even when the average of various samples is taken, which themselves are not normal, when they combine, they tend to be normal, and they tend to follow the mean of the population. So with this background, let's see what sampling is. Sampling is basically taking a small portion from a population, and which is hopefully representative, and using it to determine the truths about the larger population. Why would you take samples? Because you do not have the resources, time, and money for calculating data about the entire population. Why? Because uh, we know that from central limit theorem, it may not be actually required to take the data of entire population. Samples should be enough. And basically what you're doing is you're trying to balance your need for statistical power with the expense of gathering data by answering this question. And what the question is, how much data do you need? Well, how much data do you need? This is a deceptively simple question, but it can take many forms, and which have a lot of context. For example, how many samples do you need to determine if the average thickness of paper from one supplier is the same as another supplier? How many samples would you need from each supplier? How many samples should you take to be 95% sure that the proportion of people supporting one candidate in an election is within 5% of its true value? Can you trust the t-test conclusion that indicates the average test scores of two schools are not different? Or how many replicates do you experiment when you want to have at least 85% chance of detecting the factors that significantly affect your manufacturing process? So the questions, they can really be very, very deceptive, very difficult to answer. But at the end of the day, what you have to make sure is that you have the sample that you've collected, it is enough to give you a good approximate of the population. Ideally, you want to collect enough data to ensure that you have sufficient power to draw sound conclusions. So there are a few terms that I'd like you to remember. The first is target population. It is the population to be studied to which the researcher wants to generalize his results. So study, if you take a sample about young cricket players in Islamabad, basically you want to generalize it to the uh, to the to the group which you can call young cricket players in Pakistan, but you're taking a sample. So target population is the larger group to which you will hopefully generalize your uh, conclusions. What is a sampling unit? It is the smallest unit from which sample would be collected. So in that case, our unit would be that young boy who is playing cricket. Sampling frame, you list all the sampling units that can be measured from which you will take the sample. So your sampling frame here is the young boys who play cricket in Islamabad. Sampling scheme, the method uh, which you will use to collect samples from the sampling frame. Will it be random? Will it be non-random? We'll see different types of sampling in later slides. There are three factors that influence sample representativeness. How good your sample represents the population. The first factor is your sampling procedure. All procedures are not the same. The better your procedure is, the more representative your sample would be of the population. Sample size. The more the size of your sample, the more accurate your sample would be when you compare it with the entire population. And thirdly, participation or response. The more people respond to your questions, they participate in your surveys. Participation not in the sense of numbers only, but in the sense of their true participation, the depth with which they answer your questions. The better your sample would be representative of the entire population. So this diagram shows you the relationship between your sample, which is right in the middle, the actual data that you'll collect, which will be part of your target population. In the case of example that we talked about, it will be Islamabad's young boys. The sample is those young boys that you sampled. They are not, they're only a part of the target population. And when you draw conclusions, when you publish your results, you would hope that they are applicable to the study oblique theoretical population, which is the young boys of Pakistan who play cricket. So you should be thinking of three populations or their parts when you are taking samples. All right, so there's a term that we use, okay, so before I start getting a bit technical, I must tell you that most of what we discussed today, especially most of the difficult things that we discussed today, they may not be very consequential for everybody in this course, but they'll surely, they are very important for people who are going ahead and doing their PhD. For this particular course, you'll only need to do what I'll tell you to do on the assignment slide, on the last slide. The things that we are studying to reach that slide, some of them, they are not strictly required to do what you have to do for that slide. But if you're a PhD student, you must try and learn things in detail because you'll surely need these things when you are doing your research. Okay, so there's this thing called planning value. What is planning value? It is a priori information or knowledge, uh, advanced knowledge that you would require about your data. For example, a standard deviation of a population, or it could be anything. So basically, when you perform various tests on software, they ask you about uh, a planning value. Which value they would ask you, the test would ask you, depend on what you want to estimate. Sometimes it could be mean, sometimes it could be the standard deviation. There could be so many things for various tests. But a question that comes to mind is, if you knew everything about the population, then why to conduct research at all? So the answer to this question is that you're not expected to know the planning value exactly, but the software, when it does calculations for you, it needs some starting point to make sense of what you are about to do. And from where do you get that kind of estimate of the planning value? You can uh, get it from design specifications. For example, what is the average population per square kilometer in Islamabad? Well, we don't know, but we know the way Islamabad is designed. We know we can estimate what is the size of houses in various areas. We can estimate how many people generally live in a single house. So roughly, we can arrive at that value of average number of people living in a sector in Islamabad. Similarly, we can obtain these values from experts, the people who know this issue, whatever you are studying, in very much detail. And we can also take these planning values from previous studies. We can also do pilot studies too to make an estimate of the planning values. So while planning values are a priori knowledge, the knowledge that you would require to have before you start the study, it is not really impossible to get, or at least it's not extremely difficult to estimate. But you would require planning values whenever you are estimating your samples, you are calculating your margin of error, and so many other things. So planning value is an a priori value that you would require before conducting your research, and I'll quickly show you on a Minitab slide what does that mean. Okay, so before we move on to that, the software part, let's distinguish between sampling and non-sampling errors. So whenever you're doing sampling, there are two kind of errors that would come across you. The first is sampling error. What is sampling error? Well, it is uh, the difference between the true value of the entire population and what you have estimated because of sampling. So yeah, so think of it as uh, there's this value which would be the true value which you don't know, but there is some true value, and there's this value that you are going to estimate, which will be based on sample. So the difference between these two is called sampling error. Uh, where does it come from? Well, the first thing, it comes from the sample size. If the entire population is 200 and you have sampled the entire population, so technically that won't be a sample, but let's say you've sampled the entire population, there'll be no sampling error. The smaller your sample gets, the larger the error would get. From where other sources that this error comes from is the sample design, or the way you've planned your sampling activity, and the variability within the population. The more variability you have in your population, the more sampling error you are likely to get. Normally, the sampling error is represented by SE, or the standard error, and it is calculated by dividing the standard deviation of your sample. Uh, Standard deviation of sample, you divide it by the under root of the number of samples that you've taken. So not difficult to calculate, but the sampling error is represented by standard error, and it has to be calculated. How do you reduce your sampling error. Obviously, you can reduce the sampling error by increasing the sample size. And in cases where there are different groups or strata within your population, maybe by doing good stratification, you can reduce your standard error or the sampling error. And then there is non-sampling error. What is non-sampling error? It is all the other errors that contribute to your estimate, and some of them are non-response, people who did not respond, a badly designed questionnaire, respondents bias, processing errors, and things of the kind. They can be grouped in two sections. One is systematic error, which is called bias. An example would be that you want to target the population of Australia, but if you have administered your survey to males only, so that is kind of a systematic bias that you've introduced into your survey. And the other section is variable errors. These are the errors that can distort the results of your survey, but they tend to balance out on average. For example, non-response bias, the people who do not respond. That is kind of a that is kind of an error because your plan was to be random, and since half of the people did not respond, now you're not sure whether you're random or not, but it tends to get averaged out because every time you do, the same thing would happen. All right, so there are two more things that we'll try to understand. The first is margin of error. What is the margin of error? It expresses the amount of random sampling error in the estimation of a parameter, and it is reported in this kind of format. For example, a political poll might report that a candidate's approval rating is 55% with a margin error of 5%. This means that the approval rating is somewhere between 50 and 60. 55 plus 5 and 55 minus 5. And this 50 to 60 is called the confidence interval. How do we calculate this confidence interval? Well, it is calculated as being 1, 2, or 3 standard errors above and below the estimate. Well, what does that mean? For example, your estimate was, in the previous slide, your estimate was 55% for the approval ratings of a particular candidate. When I tell you that I'm 95% sure that my estimate is within a certain percentage, say 2, 3, 4, 5, 10, or whatever. When I say 95%, I have put 2 standard errors on each side. So if my standard error came out to be 5, I would say, uh, since I'm using 2 standard errors, it would be 5 plus 5. So I'll say 55% plus minus 10%. So I'm 95% sure that my candidate would get 55% votes plus minus 10%. Why I'm 95% sure? Because I've added the standard error twice on each side. If I add the standard error thrice on each side, I would say 99% sure. But if I add the standard error only once, I would say I am 68% sure. Why 68, 95, and 99? Because of the normal distribution. We know that in a perfectly normal distribution, 68% of the data lies within 2 standard deviations or 1 standard deviation on each side. In a perfectly normal distribution, 95% of the data lies within 2 standard deviations on each side, and more than 99 lies within 3 standard deviations of on each side of the estimate. So this is how the standard error and then the confidence interval is calculated. Okay, so the next concept is bar. We've discussed this concept in our lecture on statistics in a lot of detail, but still I'll quickly like to go through it here so that it is refreshed. Again, this is more important for PhD students. In an hypothesis test, the likelihood that you will find a significant effect or difference when it truly exists. So if you remember your statistics lecture, you had studied the Cohen's d, the calculation of Cohen's d. The power is very much related to, the effect is very much related to Cohen's d. If there is a difference between the samples, will you be able to calculate it? If yes, you have good power. To what extent will you be able to calculate it is what your testing power is. So if you look at it another way, it is the probability that you will correctly reject the null hypothesis when it is false. A number of factors, they affect your power. Obviously, the first factor is sample size. The greater your sample is, the more your power is. Then the alpha that you choose, the probability of type 1 error. Alpha, usually with the increase in alpha, your power increases. And then magnitude of population effect. If your population is very similar to each other, it will be difficult to detect a difference, obviously. And the fourth factor is variance, or in other words, standard deviation. Why? Because when the standard deviation is small or the variance is small, it is easier to detect a difference. Well, these last two, the standard deviation and magnitude of population effect, they might sound kind of contradictory to you, but if you look at the diagrams, the three figures that you see on the right side, in the first figure, the standard deviation is, it is too much. It is widely spread out. And look at both the populations that we want to study. Because they are very spread out, most of what they have is overlapping. So once it is overlapping, how would you detect the difference? You won't be able to. So populations, they have a lot of spread and they are very similar. That's why it is difficult to detect the difference between two. But if you look at the one below it, the overlap is still a lot, but it is reduced from the one above it. The standard deviation is 1.5. So we are more likely to detect a difference if there is one. And the one at the bottom, standard deviation 0.5, the overlap is really less when compared to the above two. So if there is a difference, we'll easily be able to detect it. So that is the concept of power. Now the power, it equals 1 minus beta, whereas beta is the probability of making a type 2 error. And when you increase alpha significance, you increase the power, or in other words, you decrease beta. But when you increase alpha, I mean, if that was true, that alpha increases power, then why not increase alpha to infinity? But obviously you cannot do that, because as you increase alpha, your chances of making type 1 error, it increases as well. So just to refresh what alpha is, if you look at the diagram at the right side of this slide, the red uh, part of this distribution curve, the normal curve, that is the alpha. And what is alpha? It is the significance level that you decide before collecting the data. It is just what I'm saying right now is just kind of refreshing what we discussed in the stats lecture. But this one is important, that you have to decide alpha before doing your research. You have to decide the significance level before you doing your research. If you recall, we studied examples such as in situations where life and death matters, we have to keep the alpha really low, because even if there is a slightest difference in populations, we must be able to detect it. But if it is something not very important, for example, how easily can a person buy vegetables in a certain city, well, errors won't matter a lot. There's no life and death problem there. So maybe we can live with a bigger alpha, maybe 0.9 or something, But if it is a life and death matter, it should be 0.95 or maybe 0.99. So how do you calculate how much sampling, what is the size of sample that you would require for your research? There are power and sample tools available in almost all statistical softwares. There are some available on the internet as well, and they're all of them are pretty accurate as long as you understand the inputs that you are giving to that software. So another important thing that you must remember is that for complex studies, the sample size has to be calculated for every test that you conduct. So if you look at your slide, this kind of portal from Minitab that is shown on the left side of the slide, it says power and sample size for 2 sample T test. It is not power and sample size for your complete research. It is for the one test that you would conduct. So if you'll conduct multiple tests, remember they would all require different sample sizes. So what should be your strategy? Your strategy should be that you should try to estimate the test that would require the most number of samples. That you should try to kind of predict which of my tests would require the most number of samples and find the required number of samples for that particular test, so that when you are analyzing your data at the end of your research, you don't at that point find out that your sample is not enough. You should build in a kind of margin of error in your sampling, and kind of plan for the worst possible situation at the end of the research. So you should be sampling, or your plan should be to sample for the test that would require the largest sample size. Having said that, now if you look at this dialog box, it has three entries at the top and then standard deviation. The first one says sample sizes. Well, if you have already conducted your research and you know how many samples you took, you can enter that value here. Otherwise, you can enter the other two values and find the sample size. The second thing is differences. Oh, what is differences? Well, basically, for example, if you want to see if the SAT scores or GRE scores or NTS scores of boys from one school and boys from another school are different, what is the kind of difference that you want to be able to detect? For example, if the total numbers are out of 1000, and you would say that both schools are different if their averages are at least 100 points apart. One school averages 700 and the other school averages 800. So I want to detect the difference of 100. You will write 100 here. So it really depends on what your research is. The differences that you'll enter, whatever you'll enter in this box, would be the actual difference that you want to detect. Well, the third entry that you see, it is power values. What is power? As we already discussed, it is 1 minus beta. So what is beta? It is the probability of making a type 2 error. So usually the power values would be something like zero point 0.9, 1 minus zero point 0.1, or if your beta is 0.5, 0.05, it would be 1 minus 0.05 is equal to 0.95. So it would, depending on your test, it would be between zero point 0.8 to maybe 0.95, or maybe it would be another value. But the idea is that it is the 1 minus beta figure that you'll have to enter. And what is standard deviation? Well, um, it is the standard deviation of the population. It is the planning value for this test. So you may not be, you won't be able to calculate it by the figures that you have, because it has to be given before the tests are, or before even the data is collected. It has to come from a priori sources of knowledge. For example, previous studies, for example, expert opinion, etc. If you click this options button, what you will see is a dialog box which would require you to enter the significance value or the alpha value. As I said, alpha value is kept high for very serious tests that have serious consequences, that have life and death matters. For those kind of tests, you enter 0.99, surely above 0.95, and for other tests, you can enter zero point 0.9 or maybe 0.95. So again, you must be, and you must enter significance value uh, when you click options. So in all these in all the above the three values in the upper part of this dialog box, you have to enter two, and you'll get the third value. So if you don't know your sample size, you'll have to enter differences in power value. If you've already conducted your test and you know your sample, you will know, you can find out how powerful it is. And if you know the power too and the sample size too, you can know how much difference you can detect. So moving on, there are basically two types of sampling methods. One is probability sampling and the other is non-probability sampling. When probability sampling is also called random sampling, and non-probability is also called non-random sampling. What is the basic difference? In probability sampling, every member of the population, of the target population, has an equal chance of getting selected in the sample. And in non-probability samples or the non-probability sampling methods, every uh, individual unit of analysis, every individual uh, individual uh, data that you would collect, the data point, does not have equal chances of getting selected in the sample. There are many types of probability samples. The first is simple random. The second is systematic random. The difference is that systematic sampling involves selecting items from an ordered population, whereas simple random sample uses a table of random numbers or maybe generation of random numbers from a software. So if you do not order your population, it would be simple random sample. If you order your population in any uh, sequence, it would be systematic random sample. Then is stratified random sample. Well, if you look at the diagram at the bottom of the slide, the concept of stratification is that you divide your target population in sections, and you, within those sections, then you do simple or systematic random sampling. Then cluster sampling, it is pretty much uh, it is another version of stratified sampling. It is a plan which is used when mutually homogeneous yet internally heterogeneous groupings are evident. For example, mm, uh, generally the population of Pakistan is uh, uh, very mm, accommodating of foreigners. Well, this is a generalization, and almost everybody believes that Pakistan is a very hospitable country. But within Pakistan, we know that there are clusters where hospitality is high, and there are clusters where hospitality is low. So while it is mutually homogeneous, there is internal heterogeneity. So in that situation, we'll be using cluster sampling. What is the difference? There are two types of cluster sampling. Then one is multi-stage and one is multi-phase. In multi-stage, uh, the sample units are of different types at different stages. So the first cluster that you take, it is of a different type. Second that you would take is of a different type. So maybe in the first stage you sample young people, in the second stage you sample older people, and so on. In multi-phase, the different phases observation, they relate to the sample units of the same type. So In multi-stage, you have different types. In multi-phase, you have the same type. And now that there are many other actually methods besides the ones that we've just discussed, but generally they'll be either the subdivisions of any of the ones that we've studied, or they'll be a combination of the ones that we've studied. In non-probability, again, there are many types. What is non-probability? It is a sampling plan in which every unit of analysis does not have a chance to get selected. And what are some of the types? The first is convenience sampling. It means whatever sample is convenient to you, that is being selected. The one that is closest to you, the one that costs the least, etc. Then there is purposive, judgmental, selective, subjective sample. All mean the same thing. It means that the researcher they have a particular uh, purpose in their head, and for that purpose they are collecting the data. So there's absolutely nothing wrong with it. In qualitative studies, people very routinely take selective samples because they know that the data that they require is available in a particular selection of population only. Then there's snowball sampling. What does snowball mean? It means you'll sample a particular person or whatever your unit of analysis is, and then maybe you'll ask him or her if he or she can introduce you to more potential samples, and in this way your sampling number would keep increasing, but it is not random, it is snowball. And finally then there is quota sampling. What does quota sampling mean? It is kind of stratification or clustering for non-probability samples. You kind of decide, for example, if your study is about the prevalence of diseases in different age groups, you would say that I'll take 100 samples, and the quota is that 20 of the samples would be taken from people whose age is from 20 to 30. Another 20 samples would be taken from people whose age is from 30 to 40, and so on. So you'll give quota to different age groups. It is kind of stratification or clustering, but it is in non-probability sampling. All right, so now that we've learned all these things, we'll move on to our course example, and we'll see how we uh, do different steps that are required to come up with a sampling plan. So these four things that we studied on a slide earlier, I've defined them for our course example, which was financial barriers being faced by female SME owners in Pakistan. So what is my target population? My target population is Pakistan's female SME business owners. What is my sampling unit? A single female SME business owner is my sampling unit. What is my frame? Sampling frame. Or if you look at the diagram in front of you, my target population, it is all female SME business owners in three regions, which are number one, Islamabad, Rawalpindi, number two, Peshawar, and number three, Hazara. And I'll be covering both urban and rural SME owners. So this is my sampling frame. And what is the sampling scheme? I'll try my best to be random. So uh, mm, I'll try to find out female SMEs randomly in these three areas. In these three, they'll become clusters for me. And until I can do it, and if a point reaches where sampling is not possible, then I'll start snowballing. Now remember, if you know nothing about the population or the cluster that you've planned, then you cannot go random. How can I go random if I don't know where the ladies are? What are their names? What are their businesses? So to do random sampling, you must have quite a bit of knowledge about your sampling frame. In my case, the example that I'm discussing with you, I know that the list of female business SME owners is available with SMEDA, the Small and Medium Enterprises Development Authority. A lot of data about female business owners is available in the United Nations studies. They've been conducted since 2000. Even one of them was conducted before year 2000, and they are still being conducted. So we know that right now we have about 2 million women in Pakistan who are running SMEs. We know where they are clustered, where most of them are. We even know what kind of businesses they are doing. So I have uh, good a priori knowledge to start random sampling. But if a situation comes where I cannot get data from a random women who are running textile businesses, then I'll start snowballing. I'll ask ladies to introduce me to other ladies who are doing uh, this business. So this is textile SME owners. Now, there are a few questions that you'll have to ask yourself and answer them. The first question is, will you be doing probability sampling or non-probability sampling? My answer is I'll be doing random or probability sampling until it is possible, and then I'll move on to snowballing. The second question, will I require clustering? If yes, on what basis? My answer is yes, I will require clustering. The first cluster will be on area or city basis. There will be three of them. One will be Islamabad, Rawalpindi, the second would be Peshawar, the third would be Hazara. And second clustering basis would be urban and rural. So within these three clusters, I'll be separating urban uh, women who are running textile SMEs and rural women who are running textile SMEs. The next question is, which tests are likely to be conducted on the data that I collect? Well, in my opinion, well, it's a rough opinion, but we'll see as we move on into the research. I'll be requiring one sample t-test. Why? Because there are some things about which I'll collect the data, but there'll be nothing to compare. For example, um, when I when I study the Islamabad population only, the Pindi Islamabad population only, my samples from Pindi Islamabad only, I won't be comparing it with anybody. I'll be comparing it, I'll be just collecting data about it and analyzing it. So for that, I'll require one sample T. Uh, uh, I'll also require two sample T because I'll compare Islamabad with Peshawar when I collect data from both, and Hazara with Peshawar and Pindi. So I'll be comparing them with each other. So I'll require two sample T as well. I'll require regression as well because I like to see how the data projects in the future and how much things are loading onto the the ability of a woman to sustain her textile SME. So I'll do regression as well. I'll do correlation as well because I'll be comparing the demographics, the age, the financial strength, etc., of the woman with her ability to sustain her business. So I'll require correlation is as well. Maybe I'll require some more tests as well. And why? Because I'm expecting normal distribution. All these tests they are done on normal distribution, and population planning values, they are known, as I just said, that there are a lot of studies and there's a lot of SMETA data which from where I can get population planning values. The next question, how many constructs will require separate types of statistical tests? Well, I haven't yet divided my variables into constructs, but we'll be doing it in our next session probably, which is about questionnaires. But I roughly know that I have to collect data about the endowment and financial side of that particular woman and her family. I have to collect data about her family and social uh, aptitudes toward interest and mixing with men. And I have to collect demographic data and textile subsector data as well. So there'll be 3 to 4 constructs or different areas where I'll be using different statistical tests. Now, this last one is the key question. Which construct or tests combination will likely require biggest sample? So for my case, I think the family oblique social aptitude towards mixing with men and towards interest, it would require the biggest sample. Why? Because the difference is difficult to detect. This is kind of true for most of the areas in Pakistan. Nobody likes women mixing with men, and nobody likes interest. So in this particular construct, I'll require a lot of data. Why? Because difference is difficult to detect, because the standard deviation is high and the population is similar. So I'll require a larger number of samples. So my decision is I'll calculate sample size for this particular uh, construct, family oblique social, because it requires the largest number of sample, and I don't want to be stuck in a situation where I have chosen a small sample size and I find out that it was not enough as per the power and sample size calculations in that particular case for which I required more data. So I'll calculate sample for this, and what do I need for calculating samples? I first of all have to decide for the required power, which is 1 minus beta, which would be something like 1 minus 0.9. So it would be, I'm sorry, 1 minus 0.95 or zero point 0.9. So it would be something like 0.1 or 0.05. Then I'll require difference, what kind of difference I want to detect. It will be for this particular question that I'll be asking, it will be in some kind of percentage. So maybe I'll select 10 to 20%. Another way is to calculate Cohen's d, which we studied in the statistical uh, module. And finally, I'll get the planning value from SMEDA or the World Bank studies. And moreover, I'll put the alpha value or the significance value at 0.95. It is a very commonly used value. And I'll find out what is the sample size that I need to collect data from to conduct my research effectively. So that is all I had